Hello again, we'll continue on. There are two thermodynamic definitions for entropy, and they're for different audiences, but I like them both. And they differ in the source. One of them is from Chandler's book, Intro to Stat Mech, which is a great book, and I didn't understand entropy very well personally until I could think about it in terms of particles in a box. But that's not really the point of the course that we're in now. But first we'll start with this, because conceptually it just makes a lot of sense. There's this general tendency to increase disorder. For instance, the whole coffee cup example, where you're mixing things, or maybe you're making a cocktail where you shake it and try to unshake it. Good luck with that. So what the definition is from the Chandler book is that there is an extensive function. Of course, extensive means the type of variable that it is, an extensive as opposed to an intensive variable. So this is something that depends on the size of the system. There is an extensive function of state. So you need two state variables to define a system. And they defined it as entropy, S, as a function of the energy that goes into it, and the mechanical extensive variables, for instance, like pressure, volume, etc., which is monotonically increasing function of energy, and that if state B is adiabatically, what does adiabatically mean? Adiabatically accessible from state A, then this entropy of state B must be greater than or equal to the entropy of state A. Adiabatically accessible means no energy flows across the overall system boundaries. Heat, the temperature. And the theoretical way that you can think about the adiabatic system, adiabatically accessible, you can go through irreversible process or reversible. We'll describe a bit more of what that is in a minute. And here you'd have, clearly, if it's irreversible, state B has to be greater than state A, which means that this entropy of state B, or this function at state B, minus state A, has to be greater than 0. Whereas if it's a reversible process, then B to A could be carried out. So if that's the case, then you can say that state A has to be greater than or equal to entropy in state B. But if it's reversible, then you can say the reverse, that the entropy in state A is greater than or equal to that in state A. And so you combine these two. The only solution to that is if the entropy in A is equal to the entropy in B. So the subtraction of the two, would it be equal to 0? And so the combination of these two together gives you that delta S adiabatic, combining this to this, means that this overall has to be greater than or equal to 0. So this is the basic definition of entropy from the concept of disorder. Next, we'll go to a more engineering derivation, a bit more pragmatic definition for entropy.